So, simple harmonic motion and circular motion. We were trying to connect those two chapters together. There is a good relationship between circular motion and simple harmonic motion. That's what I started explaining. Simple harmonic motion, simple motion is mostly in one plane. Oscillation in one plane is a simple motion. Harmonic means rhythmic, having a certain time period, having a certain frequency, maintaining a certain rhythm, all that stuff. So the connection between circular motion and simple harmonic motion, I gave you the idea of something going round and round. So if an object is going round and round about a certain radius, and if you shine light from one side, if you shine light from one side, a parallel beam of light, and if you have a screen over here, on the screen you will see the shadow of that. You will see the shadow of that object which is sticking out like that over here. So taking this as a reference point and taking this as the mean position, as this goes round and round, moving with a certain angular velocity. So this is angular velocity. Angular velocity omega. So what's happening is this object moves from place to place. When this object moves from here to here, the shadow will move from here to there. And what is this height? What's it called? Amplitude. That's called the amplitude. And when this comes all the way here, the shadow will come back to the same mean position. And when this object goes here, it goes to the bottom here. That's also another amplitude. And come back again here, returns to the mean position. So when this object goes round and round, this one goes up and down. Can you see that? When this goes round and round, that goes up and down and back. So for one complete circular motion, this one executes one complete simple harmonic motion. And this object, when it goes one full circular motion, it describes an angle of 2 pi radians. The complete angle is 2 pi radians for a circle. And this is also executing a certain angle, but it's called, what's the angle called?
Phase angle.
Phase angle. Yeah, this also goes through 2 pi radians, and that is a phase angle. So it's a first phase, a second phase, third phase, and fourth phase. So each phase is like pi over 2. So pi over 2, pi over 2, pi over 2, and pi over 2 makes it 2 pi. Is it okay? And here, pi over 2, another pi over 2, another pi over 2, another pi over 2. That's totally 2 pi radians. So you can see the connection between circular motion and simple harmonic motion. So if you see something spinning like that, the shadow will be moving up and down. So if I'm going to move my hands like that in circles, and if light is made to shine, the shadow of my hands will go up and down. So, as I said again, if something that's spinning that way under light, the shadow will look like as it's going up and down. Now, if this object is going only up to here, say some position here, the shadow is going to go here. Now, the connection between this is what is known as a displacement. Y is called the displacement. Y is a displacement. Where's the displacement on this picture? That's a displacement. The vertical shift. The vertical shift, right? That is the displacement. Now, how do you get that displacement? When you know that this is the radius and this is the angle theta, what is y equal to? Y is equal to r sine theta. Y is equal to r sine theta. That is the displacement in terms of the radius. Same thing applies here. Y is equal to r sine theta in simple harmonic motion. What is theta standing for?
Measurement of the angle.
What angle is it called? Phase angle. That's called phase angle. And what's the relationship between omega and theta and t? Omega is theta over t,
Theta
which is same as 2 pi over capital T, which is same as 2 pi f. You can see all of those are connected. So omega is theta over t. What is theta then? Omega is theta is omega t. Put that here. Y is equal to r sine omega t. That is your equation for displacement in simple harmonic motion. So at any time, if you want to find out where is it? At any time, if you want to find out where it is, substitute. What is r standing for?
Radius.
Amplitude.
Yeah.
R stands for amplitude. So switch off your circular motion completely, because we're not going to talk about radius. We're not going to talk about anything else. We're not going to talk about angular velocity also. We are completely off from there. Now we are switching completely to simple harmonic motion.
But that has angular velocity in it.
What is R standing for?
Amplitude.
What is T?
Time.
What is omega?
Angular velocity.
It's not called angular velocity anymore. It's called angular frequency. It's called angular frequency. And what is omega? Omega is 2 pi f. This is called angular frequency. And this is called frequency. What is the angular frequency's unit? What's the unit of this? Angular frequency's unit? What's the angular velocity's unit?
Second.
Radians per second. So angular frequency's unit is radians per second. Same thing. It is just called differently, but it's still the same angular velocity concept. The only thing is this is not really moving through an angle, a physical angle. It's called a phase angle. This one's unit is hertz. So frequency is measured in hertz, and this is measured in radians per second. So this is radians per second, and that is hertz. Get it? Okay, so that's your equation for displacement in simple harmonic motion. R equal to sine. When I say omega t, omega and t are together. Okay, just make sure. It's not like sine omega then times t. It is sine omega t, because that's the phase angle. Theta is omega t. Any questions on the displacement? Good. Now let's go to the next one, which is velocity. Velocity. Before going to velocity, let's draw the graph of displacement with respect to time. Displacement with respect to time.
Is that a wave?
Say it again.
A wave?
Yeah. Displacement with respect to time. So at time t equal to 0, put time t equal to 0 here. What do you get y as?
0.
Y is equal to 0. That means you're here. You're here. This point. At time t is equal to t over 4. Means 1/4 of the time period. For this to go up, down, back down again, then here, that is 1t. So t over 4 means you're going up to here, right? So how do you check where it is? Y is equal to r sine omega t. R sine, instead of omega, I'm going to write it as 2 pi over capital T. And time t, I'm going to write it as t over 4. So this t and t cancels off. So what is left in this bracket?
2 pi over 4.
Which is
Pi over 2.
sine pi over 2 is? Sine pi over 2 is?
1.
1. And so you get y equal to r, which is why it is here. You get it? So on this graph, that is t over 4, and the object is going to be there, and that is the amplitude. What's going to happen at time t is equal to t over 2? half the time period. So do that again. Y is equal to r sine 2 pi over capital T times T over 2. Let me know if you don't understand something. Y is equal to r sine 2 pi over 2 is pi. What is sine pi? Now when you do this on the calculator, put your calculator in radian mode. This is one place where you will use the radian mode more than degrees. Okay? Because we are talking all in radians. So sine pi is 0. So you get y is equal to 0. That means it is back again here. So at t over 2 it is here. At time t is equal to 3t over 4. Y is going to be equal to r sine 2 pi over capital T. You know why I'm writing 2 pi over capital T? Because that's the same as omega times 3t over 4. Cancel the t's. So you have 6 pi over 4, which is same as 3 pi over 2, which is like 270 degrees, right?
Yeah.
So what is it? -1. So you get y equals -r. So at time 3t over 4 is going to be here at -r. And then when at time t is equal to t, when the time is fully t, then you get y is equal to 0 once again. So you go back to 0. So you get a sinusoidal graph. So the displacement graph is going to look like this. It's a sine wave. And you can easily understand that from the looks of this equation, right? Y is proportional to the sine of the angle. So automatically it's supposed to be a sine curve. So that's your sine curve. Any questions here? Good. So you can see the sine curve clearly coming up. Now if I ask you, all right, at this particular time, at a time of 0.397 second times t, where is it? So all you do is substitute that here and get the answer. So you can actually figure out where the object is at any definite time. You get it? By just using that equation. So these are equations of motion for simple harmonic motion. These are like equations of motion for simple harmonic motion because it tells you exactly where the object is at a definite time. Now let's go to the velocity part of it. The velocity part of it. Back to the same drawing. The object is here. How fast is it moving? How fast is it moving? If it is moving with a certain angular velocity omega, how fast is it moving? What's the tangential speed? What's the tangential speed in circular motion? Go back to circular motion in your books. You do have a relationship there. How fast is this moving? Turn your pages backward to circular motion. Tell me that equation quickly. That's a very important equation you must have boxed. That's the connection between linear velocity and angular velocity, yes. R omega. So this V is R omega. That's the relationship between tangential speed and angular speed. Do you get it? So V is equal to R omega. Which way? This way. So if this object is moving in that direction, when the angle is theta, the shadow is going to move which way? Upward. Will the shadow also move with R omega?
Yes.
Yes.
Yeah.
When this is moving in this direction with R omega, will the shadow be rising up with that same velocity? No, only a component.
Yeah. It's
Only a component. So you have to split this velocity into two components. One is this way and the other is this way. So this velocity is this. Only the vertical component. So you need only the vertical component. So what's that vertical component?
Or the B side theta.
Yeah. So this is okay. This is theta. What is this angle? Theta. If that is theta, what is this? 90 minus theta.
Yeah.
And what is that then?
90 minus
90 minus theta, which is theta. So this angle is also theta. So if the velocity is r omega in this way, what is the velocity this way?
R omega sine theta.
No, cosine.
And vertical sine.
Maybe you're getting confused with this. All right.
Right.
This is v equal to r omega. If that is v equal to r omega, you want this component, which is the adjacent component for the angle. So that's going to be r omega cosine theta. Right? So with what velocity is this going up? With the velocity which is r omega cosine theta. Cosine theta. So if I write it down, v is equal to r omega cosine, instead of theta I'll write omega t, and that is your equation. That's your equation for instantaneous velocity. Velocity at any instant. All you do is just plug it in. Velocity at any instant, just plug it in and you get the answer. When time t is 0, this thing is over here and the shadow is right here. When time t is 0, what is cosine 0? So what is the velocity? That is the maximum velocity, which is r omega. So the maximum velocity in simple harmonic motion is r omega. What is r? Amplitude. What is omega? Angular frequency. Angular frequency. So this is your maximum velocity. That is when time t equals 0. So where is it going to be fastest? When it's crossing this point, it's going to be fastest. Where is it going to be 0 velocity? At the top and the bottom. It stops and turns back. At the top and bottom, when it's moving like this, fastest is right there. At the top and bottom, it is stopping and turning back, right? So it has to be 0 here, 0 here. Now if you plot this graph on the same thing here, so this is a displacement equation, y equal to r sine omega t. How is the velocity graph going to look like? When time t is 0, the velocity was?
0.
No. When time t is 0, the velocity was the highest. So it's the highest velocity, r omega. So it starts from here, goes to 0. It's a cosine curve. You can see the equation is cosine curve. Right? So y is equal to r sine omega t, but velocity is r omega cosine omega t. And it's a cosine curve. So where is the object fastest at the mean position? And what's the fastest speed? That one. That's the fastest speed. R omega is the fastest speed when something is moving in simple harmonic motion. Now, can we get this equation by differentiation? Yes, we can. Now, most of you are doing differentiation, right?
Yeah.
If you're doing differentiation, you should know this, that if I differentiate this equation, you should get the velocity.
What is differentiating?
That's a long story.
Calculus.
So, if I want the velocity, if I want to find the velocity is dy over dt, right? So I'm showing you a differentiation method of getting the same equation, but don't worry if you don't know differentiation. Forget about it. There will be a time when you come to know about it. So d of r sine, I'm going to call it theta. I'm not going to call it omega t right now. Over dt. R is a constant, I can pull it out. So R is a constant, I pull it out. And then you have d of sine theta over dt. And of course, you cannot differentiate this because there's theta here and there's t here. So best thing to do is to split it up. R differentiate sine theta with respect to theta and then multiply d theta over dt. So this is basically the same as this. I've just introduced a d theta here and d theta here, right? Get it? So what is differentiation of sine theta with respect to theta? Cosine theta. So it becomes r cosine theta. And what is d theta over dt? What is theta over t? Omega. So times omega. So that becomes this. You get it? So r omega cosine theta, which is the velocity, which is this. You get it? So yes, you can derive velocity from displacement. All you do is differentiate it. Now, I didn't show you the differentiation first. I showed you how to split this into components. And you understand that, right? So I use the component method of getting the same thing. Now here's a way to differentiate and get the same thing. So you can derive it both ways. Now let's talk about acceleration. Acceleration in simple harmonic motion. Acceleration. I'm going to take these off now. When this object is here, when that object is spinning in that manner, what acceleration does it experience? What do you call that acceleration? Centripetal acceleration. And how much is it? What's the equation for acceleration? R omega square, or v square over r, right? We'll prefer to use r omega square because we want the omega in. So, which way is the centripetal acceleration? Towards the center. So the centripetal acceleration is towards the center. And how much is it? R omega square. The centripetal acceleration is towards the center, which is r omega square. Now, when this object is having an acceleration towards the center of the circular path, is this shadow accelerating?
No.
It will be accelerating. Which way? Downward. Because if we split this into two components, this acceleration can be split into two components, one that way and one that way. And this acceleration is not going to be seen on the shadow. That's horizontal. Anything horizontal is not going to be seen. The vertical acceleration, this one, is the acceleration of this. So the acceleration of this shadow is going to be downward by the same amount. Now how do you resolve it? This is theta, that is theta, correct? What is this component of the acceleration? R omega square cosine theta. And what is this one?
R omega squared sine.
And which way is it? So I'm going to put the minus sign because it's already downward. So acceleration in simple harmonic motion is minus r omega square sine theta. It is minus. Why minus? Because I brought this minus in because it is pointing downward. When the displacement is positive, acceleration is that way. What kind of a graph can you expect with that for acceleration? Negative sign. So the graph is going to look like this, opposite of this red. Okay, opposite of the displacement graph. It's just the opposite of the displacement graph. Again, we can write it as acceleration is minus r omega square sine omega t. That is your acceleration in simple harmonic motion. What is the acceleration at time t equal to 0? 0. At this point, no acceleration. That means when it is swinging by the mean position, there is no acceleration right there. Where's the acceleration most? When it is turning back. So what is the acceleration at that point? So if you put t as t over 4, you'll end up getting what? What is the maximum acceleration in simple harmonic motion?
R omega.
R omega squared. Well, the minus sign is there just to let you know it is opposite. But this is your maximum acceleration expression. That's your equation for maximum acceleration. Are you getting the connections?
Mm-hmm.
And you can also derive this by differentiation. I'll show you that. Velocity is r omega cosine theta. If you differentiate velocity with respect to time, you get acceleration. So you differentiate this with respect to time. So you get r omega as a constant. So it's d cos theta over dt, which is same as r omega d of cos theta over d theta times d theta over dt. So you get r omega. What is cosine theta's? Negative sign. And what is that? And so you get this. Alright? So if you differentiate velocity, you automatically get this equation, and the minus sign is automatically coming in. You don't have to introduce it now. We introduced it because we went by the physical meaning there. Now look at this equation again. Look at that equation again. I know it's a lot of equations, but it's all important. Look at that equation again. A is minus r omega square sine omega t, right? What is that part alone? What is the stuff that I just enveloped? That's y. R times sine omega, that's displacement. So what A is minus omega square y. Now that tells you the acceleration with respect to y, not time, but displacement. So if you know the position, you should be able to say the acceleration by that equation. By position, you can find the acceleration. You know why the acceleration graph and the displacement graph are opposite to each other? Look at that. Right, the minus sign here. So acceleration is directly proportional to the displacement, but opposite. Okay? And this is where we define simple harmonic motion. So write down the definition of simple harmonic motion. This is the definition of simple harmonic motion. So write down the definition now. Write down the definition of simple harmonic motion. I'm dictating it. Just write it down. Simple harmonic motion is a periodic. Simple harmonic motion is a periodic to and fro motion It's a periodic to and from motion, basically to and from. Simple harmonic motion is a periodic to and from motion of an object such that its acceleration such that its acceleration is directly proportional to I'll say it again. Simple harmonic motion is a periodic to and from motion of an object such that its acceleration is directly proportional to its displacement from the mean position. Acceleration is directly proportional to its displacement from the mean position. And is always directed towards 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 the mean position. That is the complete definition of simple harmonic. So if you see an oscillation which is following this rule, then that is simple harmonic. That is simple harmonic. Now, is this simple harmonic? Is this simple harmonic?
No.
Why no? Because there's nothing to do with this equation at all. What is the acceleration of this ball when it is in the air? Always the same, right? Does it depend on where it is? No. And it definitely suffers a positive acceleration when it hits the floor. So this is not simple harmonic motion. So when a ball bounces like that, that's not simple harmonic motion. For simple harmonic motion to be called simple harmonic, it needs to follow this thing what I said just now. Acceleration should be directly proportional to the displacement from the mean position, and it should be directed towards the mean position. It should be directed towards the mean position. That is the rule. So if this is an oscillation that's going on like this, when it's here, the acceleration is 0 because there's no displacement. When it's here, which way is the acceleration? When it's here, which way is the acceleration? Right? And that's the reason why it goes and stops and comes back. Why is it trying to return back to the mean position? It's because the acceleration is directed towards the mean position. Now, putting all these equations together, right? I'm writing down all the equations now. Y is equal to R sine omega t. V is equal to R omega cosine omega t. V max is R omega. Acceleration is minus R omega square sine omega t. Acceleration max is R omega square. Acceleration is also minus omega square y. So these are all equations that you just come across. So, if I tell you the time, can you find the displacement? If I tell you the time, can you find out how fast it's going? If I tell you these two, can you find the max velocity?
Yes.
If I tell you the time, can you find the acceleration at that particular time? You can find the maximum acceleration. If I tell you which position the object is, can you tell me the acceleration? Now if I tell you the position, can you find the velocity? There's no equation there. You can mark your way through it. Yes. I'll show you how to do that. So how do you get velocity from position? So you must have known this trigonometric identity. Cosine theta is square root of 1 minus sine square theta, right? You seen that? Because sine square theta plus cos square theta is 1. Cosine theta is that. Which means this can be substituted in terms of sine theta. So let's do that. So V is equal to R omega square root of 1 minus sine square theta, right? Now what is sine theta? What is sine theta? y over r. So I'll put it as so v is r omega square root of 1 minus y square over r square. And if you take the least common multiple, that's r square, and then it will be r square minus y square. What is under root r square? What is the radical of r square? R, and there's an r here, so those two can cancel, right? So what is left here is omega square root of r square minus y square. That also is an equation which will tell you clearly where, how fast the object is moving when you're told the position. Do you understand that derivation? Yes, no, maybe? If you don't understand this, I'll show you another way of getting it. A simple trigonometric way of getting it. Simple way of getting it. Look at this. Y equal to r sine omega t. So I'm just creating a triangle. That's the angle theta, which is your omega t. Sine omega t is what? Y over? What is sine omega t? Y over r, which is opposite over hypotenuse. So if that is y and this is r, what is this? What if the hypotenuse is r and that's y, what is this? Square root of? So what is cosine omega t? Square root of r square minus y square over r. Put that here and you get this. That's another way of looking at it. So I'm not using an identity now, I'm just using a simple trigonometric ratio. You see it? When you plug that here, the r's will cancel off and you end up getting this. Now let me give you a problem. I'll get started with the problem and then you do it. Here's the problem. I'm clamping this meter stick on the table, and I'm just going to push this end down by 10 centimeters. And it's going to oscillate. See? I pushed it by 10 centimeters. What's the 10 centimeters then? The R, the amplitude. So when I do that, the frequency is around 5 hertz. I'm going to give you that. So here's the problem. That's a meter stick that is clamped on the table. Okay? And this meter stick is made to oscillate with an amplitude of 10 centimeters. And the frequency is 5 hertz. The frequency is 5 hertz. What is omega? What is the angular frequency? Find this out. What is the angular frequency? You should be able to do it fast now. What is the angular frequency formula?
2 pi f.
2 pi f, put it down.
10
2 pi times 5, which is 10 pi. Now remember to use the pi on the calculator all the time. Don't make it shortcut as 3.14. That is totally wrong. Leave it as pi and pull it out from the calculator always.
So what do you want to know?
Just the angular. So what is this? Radians per? Next question is, what's the maximum speed? How fast is it going when it is here? When the meter stick is moving, how fast is it moving when it is zipping past the mean position? What's the formula? R omega.
0.1.
So, yeah, change your amplitude to meters. 0.1 times 10 pi, which is how much? Pi. Radians per, no, sorry, meters per second. Yeah, so it's basically 3.1, all that meters. That's how fast it's going. We don't realize it. It's going really fast when it's hitting the main position. Where is it after a time of, tell me where it is, after a time of 3.637 seconds. Where is it? Where is this meter stick? The tip of the meter stick. So what do? Use that equation. Y is equal to R sine omega 10 pi times t.
Meters.
So it's 0.0, is it positive?
Yes.
Your calculator must be in the radian mode.